Welcome back, class. So, we've been talking about concavity, and now we're going to do some examples of using the facts we learned about how concavity relates to second derivatives to decide where this function is concave up and concave down. So I've now given you this formula up here for the function, and so now we're going to use our information about the second derivative to figure all of this stuff out. Okay. Now, before we even do that, you can certainly, sorry about that, you can certainly look at the graph and you can guess from the graph that probably it's concave down over here and it's concave up over here and it's got an inflection point here in the middle. But I want to make sure we can do that algebraically by manipulating this equation so that when the graph makes it a little less clear, we'll still know what we're doing. Okay, so as indicated, we definitely need the second derivative. So let's calculate the second derivative of this first. So that's 3x squared minus 3. That's the first derivative. And this 6x, that's the second derivative. Okay, so we can look at this. And so the first kind of question I want to talk about is how you'd answer it if someone just asks you, hey, is this graph concave up or concave down at x equals 2? Okay. Now, again, in this case, I want to point out, we can look at the graph and sort of guess. It's definitely concave up there from the graph. But we can now do that algebraically, because what I can do is I can put 2 here into the second derivative and get 12. And that's positive. And remember, positive second derivative means concave up. Okay. Likewise, if you picked, say, minus 2, f double prime of minus 2 here would be minus 12. And so there it is concave down. Okay, so and you can see that again in the graph. So that's how we can decide, just for any function at any point, hey, is the graph concave up there or concave down there? And that's one question you might be asked. You might also be asked, where is the function concave up and where is the function concave down? In which case, we're looking for intervals. And this should remind you of the intervals we gave for increasing and decreasing. And so again, it's concave up where the second derivative is positive. Well, the second derivative is just 6x. So 6x is positive exactly when x is positive. So this thing is concave up on the interval 0, infinity, and it is concave down on the interval minus infinity to 0. Okay. So you might also be asked for that. You might also be asked for the inflection points. That is where the function changes concavity. And so in this case, the inflection point here happens at 0 because 0 is the x value where this function changes from concave down to concave up. And so my inflection point here I get is 0, comma, and then I put 0 into the original function, so it is 0, comma, 4. Okay. Do note, just as a point of potential confusion, these two ordered pairs, they're intervals, whereas this is a point. It's that point specifically. Okay. Now, in parallel to this, just to be thorough, I want to make sure we also remember how to do the stuff with increasing, decreasing, and turning points. So I want to basically remember how to do the first derivative test. Okay. So the first derivative test here is all about, well, not surprisingly, the first derivative. So when we sit down to do the first derivative test, we figure out, okay, where are the critical numbers? That is, where is 3x squared minus 3 equal to 0? Which is to say, where is x squared equal to 1? This is to say, x is plus or minus 1. Then we draw out our little number line. And so we make our point here at -1, and our point here at +1. And then we can figure out what's happening. And so we can look at the graph and figure out, okay, so these are the two critical points, that one and that one. Those are the two places where the graph is horizontal. And I can see that it's increasing over here, then it's decreasing here, and it's increasing back over here. So the function looks like increasing, decreasing, increasing, like that. And so I can report that this function is increasing on -infinity to -1 and 1 to infinity, and it is decreasing on -1 to 1. Okay. Finally, you might be asked about the turning points. Okay, and the turning points, those are, again, the points where the function switches from increasing to decreasing. So in this case, there are two of them, and they correspond to this x equal -1 and this x equals 1. I should specify or clarify. It's where it switches from increasing to decreasing or decreasing to increasing. So they happen at these two x values. Okay. And then to get the y values, I come back up here to the original function. And so I put in -1 here, and so I get -1 plus 3 plus 4, so that will be -1, 6. And then I put 1 into the original function, and so I'll get 1 minus 3 is -2 plus 4 is +2. Okay, and so those are my two turning points, again, in the graph. Oops, sorry about that. In the graph, they are here. That's where it changes from increasing to decreasing. This is where it changes from decreasing back to increasing. Okay, so most questions won't ask you all of those things. Most questions will ask you some combination of those things. So they might ask, on what intervals is this function increasing? Or on what intervals is this function both increasing and concave down? Or is it concave up or concave down at these points? Or what are the x and y coordinates of the inflection points? Or what are the x-y coordinates of the turning points? And so each question will ask you some subset of those. And I'll go ahead and I'll do a few more videos where we'll go over examples of finding that with slightly more complicated functions, just so we can practice with the derivatives and remember stuff about solving trig equations. But until next time, be well.